The next rule is the quotient rule. So this is analogous to the product rule. It covers the situation where one function is the quotient of two other functions. So the rule, which I realize is quite large, is if h of x equals f over g of x equals f of x over g of x, then h prime is g of x times f prime of x minus f of x times g prime of x over g of x squared. I realize that this looks kind of asymmetric. It looks as if there's something wrong with the idea that a g squared ought to be in the denominator. It just comes out of the mathematics. This is just what the rule is. There's a proof that this is the correct rule. I don't want to go through that proof. Perhaps an easier way to remember this, just like with the product rule, is to drop all the x's out of the expression and just remember it as gf prime minus fg prime over g squared. Note that the order does matter because for a difference it does matter which order you subtract in, and of course you have to know which one of these is that f is on top and g is on the bottom, because otherwise you're going to end up squaring f, which would be the wrong thing. So the rule is gf prime minus fg prime over g squared. Let's see an example of how this works. So if h of x equals 3x to the 8th, so over x cubed plus 5x, let's calculate h prime of x. So in order to do that, let's observe that f of x is equal to 3x to the 8th, and g of x is equal to x cubed plus 5x. So in that case, f prime of x is equal to 24x to the 7th. So just recall you bring the exponent down and then lower the exponent by 1. So we have 8x to the 7th, but we had a 3 in front of it, so that's where I got the 24. So g prime of x is going to be 3x squared, and this is going to be, we haven't done one of these yet actually, where the exponent is 1. So x to the 1, its derivative is going to be 1 times x to the 0, and since x to the 0 is just 1, that means that the derivative of x to the 1 is 1. So this is going to be just 5 times 1x to the 0, or 5. So it's actually a rule that's worth remembering, just as an aside, is that if f of x equals ax, then f prime of x equals a for any constant a. So that's just worth knowing. Anyway, all that to say the derivative that g prime is equal to 3x squared plus 5. So let's go back to calculating h of x, h prime of x. And go back up here and see what the rule is. It's gf prime minus fg prime over g squared. We can pretty much read what we need off of this table. So this is going to be equal to g, which is x cubed plus 5x, times f prime, which is 24x to the 7th, and then minus fg prime, so that's going to be minus 3x to the 8th. G prime is 3x squared plus 5, and then we put all of that over g squared, which is x cubed plus 5x squared. Write that exponent 2 a little nicer. There we go. So that is h prime of x. I'm just going to put up here the shorthand for remembering the product and quotient rules. So for the product rule, remember that if you have a function that is just f times g, its derivative is fg prime plus f prime g. And if you have a function that is f over g, then its derivative is gf prime minus fg prime over g squared. So that's the kind of short way to remember these rules. The next rule is the rule covering the exponential function f of x equals e to the x. This is one of the nicest rules of all, and it's very simple. If f of x equals e to the x, then f prime of x equals e to the x. In other words, e to the x is its own derivative function. That's a really nice rule, and it also demonstrates kind of how remarkable the number e is. You may wonder, why do we make a big deal about this number e, which is approximately equal to 2.718? And the reason, of course, is, well, there are several different reasons, but one of the reasons is that when we use e as the base of an exponential function, then e to the x is its own derivative. So I just have an example here of how we would use that. Of course, there's no way to give a function, to give an example. It's just, here's the function f of x equals e to the x. What's its derivative? Because we already stated that up here. So let's just use this fact as part of finding the derivative of another function. I have f of x equals 7x to the 100 plus 3 over the cube root of x plus 4 e to the x. So what is what is the derivative of that function? First of all, let's just write this. We just want to write this in power form. So this is going to be 7x to the 100 plus 3x to the negative 1/3. That's what it means when we divide by the cube root of x. That's like x to the negative 1/3, and then plus 4e to the x. So what we know from the linearity rule is that we can simply add all these derivatives together. So the first one is going to be 7 times 100x to the 99. So that's going to be 700x to the 99. And then here we've got 3x to the negative 1/3. So I'm going to have 3 times negative 1/3 x to the negative 1/3 minus 1 is negative 4/3. And then plus 4 times the derivative of e to the x is just e to the x. So this is going to equal 700 x to the 99 plus, sorry, minus x to the negative 4/3, and then plus 4e to the x. Sometimes, by the way, you're asked not to put any negative exponents in the problem, in which case we could easily just rewrite this in this form. This would be minus 1 over x to the 4/3, and then plus 4e to the x. So there we go. Either of those should be acceptable. Okay. By the way, some people often ask why there has to be a special rule for e to the x. Many people sort of look at it and say, well, wait a minute. If I have f of x equals e to the x, then isn't it the case that f prime of x by the power rule would just equal x e to the x minus 1? Is that true? Well, of course it's not, because we have a special rule for it. But the thing to note here is that the power rule, the one that says that we can use nx to the n minus 1, that only works when the x is in the base. Here, when the x is in the exponent, we need different rules for it. So that's one way to understand why this is different. It's very common that people try to apply this rule when the x is in the exponent, when the variable that we're differentiating with respect to is in the exponent, but it doesn't work that way. So you can't do that. So the next set of rules covers the trigonometric functions. The most basic of these are the derivatives of sine and cosine. So the first one is if f of x is sine x, then f prime of x is cosine x. The next one says that if f of x is cosine x, then f prime of x is negative sine x. I've put here the derivatives for all of the different, for all of the 6 trig functions. In addition to sine and cosine, we have the derivative of tan x is secant squared x. The derivative of secant x is secant x tangent x. The derivative of cotangent x is negative cosecant squared x. And the derivative of cosecant x is negative cosecant x cotangent x. Now, the truth is, you really do need to commit these all to memory, but there are a couple of different things that can kind of help you do that. First of all, the sine and cosine rules are kind of easy to remember. The second thing is that if you look at the 3 cofunctions, cosine, cotangent, and cosecant, these are the 3 functions whose derivative begins with a minus sign. The next thing to note is that there's a certain symmetry here, like the derivative of tan is secant squared. The derivative of cotan is cosecant squared, and there's kind of a similar relationship for secant and cosecant. So these rules aren't completely random. The other thing to realize is that if you happen to forget them, really you only need to know the derivatives of sine and cosine, because although it's kind of a long way to do it, you could derive any of these others from the derivatives of sine and cosine, since all the other functions are actually just defined in terms of sine and cosine. So just for example, let's suppose that you really can't remember the derivative of secant. So you say, what's the derivative of secant of x? This is, by the way, another way of writing, say, differentiate secant x or find the derivative of secant x. You can write this symbol. We covered that symbol in a previous lecture. Anyway, the derivative of secant x, if you can't remember it, is just equal to the derivative of 1 over cosine x, because that's how the secant function is defined. But this is a quotient function where f of x equals 1 and g of x equals cosine of x. So f prime of x by the constant rule is 0, and g prime of x by the rule that we covered above, derivative of cosine is just negative sine. So that means that the derivative of 1 over cosine x is just going to be gf prime by the quotient rule. So that's going to be cosine of cosine x times f prime is 0 minus fg prime, which is 1 negative sine x, and then over g squared, which is going to be cosine squared x. So that gives us 0 minus negative sine. So that gives us sine x over cosine squared x, which equals 1 over cosine x times sine x over cosine of x, which equals 1 over cosine is secant x, and sine over cosine is tangent x. So just like we have up here, the derivative of secant is secant x tangent x. So you can derive any of these using the sine and cosine rules as long as you remember those, and as well as other rules such as the quotient rules here. Let me just put up another example of something we could do. Let's find the derivative of sine x cosine x. So note that this is going to be a product. This is a product of two functions. We might call that f and we might call that g. So recall that the derivative is just going to be fg prime plus f prime g. So remembering what the derivatives of the trig functions are, we have sine x times the derivative of cosine is negative sine x, and then plus we have the derivative of sine, which is cosine of x. Write that a little neater. And then times g, which is cosine of x. So this is equal to cosine squared x, and then we have sine x times negative sine x is minus sine squared x. And you might recall, this is a perfectly valid form of the answer, but you might recall that cosine squared x minus sine squared x is equal to cosine of 2x, which is also an answer. The next rule is the derivative of the natural log function. So that's the function ln x. And that rule is if f of x equals ln x, then f prime of x equals 1 over x. The way I thought I'd demonstrate that is in combination with the product rule and a trig function. So let's suppose we want to find the derivative of ln x times tan x. Recall that this symbol d over dx, it refers to a derivative, so this is commanding us to differentiate the function ln x times tan x, or find the derivative of ln x times tan x. So anyway, so here what we have is we have a product function. We can call that f and we can call that g. If we do, then that means that the derivative of their product is going to equal ln x times the derivative of tangent is secant squared x, and then plus I have the derivative of ln x, which is 1 over x, and then I multiply that by tan x itself. So anyway, that's the derivative, and that makes use of of what we know as the derivative of the natural log function.